We now consider the Aldol condensation, which is one of the most important reactions in all of organic chemistry. So the reaction that we will use as an example of how this works is the reaction in which two molecules of acetaldehyde react under basic conditions. In this case, we're going to look at it using sodium hydroxide as a base to form 3-hydroxybutyraldehyde. So as I already alluded to in a previous video, the product of this reaction is a beta-hydroxyaldehyde. And the reaction name aldol comes from the fact that the product features both an aldehyde and alcohol functional groups. So this particular reaction is a dimerization of the starting material, but as we will see, not all aldol condensations are. So let's dive right in and look at the mechanism of this reaction. So we are under basic conditions. So what that means is that in the first step, we're going to deprotonate the hydrogen from the carbon alpha to the carbonyl, what we call the alpha hydrogen, using NaOH as the base. And this will give us the now familiar enolate ion. So this particular proton transfer reaction, if you're looking at your pKa tables, you may be scratching your head a little bit because it is unfavorable by 3.5 pKa units. pKa of water, which is the acid on the right side of the expression, is 15.7, and the pKa of acetaldehyde is 19.2. The fact that it's unfavorable means that at equilibrium, the equilibrium will favor the reactants rather than the products, but you will still have some amount of product, specifically of enolate, present at equilibrium. And given that that enolate is going to go on and react in a subsequent step of the mechanism, you don't actually need to have a lot of it present in order for it to react. Think back to mechanisms where you had a carbocation intermediate. You would only generate a small amount of the carbocation in the first step, but then that would go on and react further in subsequent steps. Okay, so the next step, once we've generated the enolate, is that the enolate adds as a nucleophile to the carbonyl carbon of another molecule of acetaldehyde. And obviously, if we have only generated a small amount of enolate, we have a lot of acetaldehyde there for the nucleophile to react with. The product of this step now is an alkoxide anion, and this step will be favorable for pKa reasons because the alkoxide anion is the conjugate base of an alcohol. Its conjugate acid would have a pKa of about 16. However, this step is unfavorable for entropy reasons because you have two molecules coming together and making one molecule without kicking off any other piece. So enthalpy, yes, entropy, no. They're going to end up balancing out, so delta G for this step is going to be close to 0. Then step 3, which is also going to have a delta G fairly close to 0, is the protonation of the alkoxide to give a neutral alcohol as the final product. In this case, we're saying that water, probably the water that you generated in step 1, is the acid that you're going to use in this case. So you're taking an alkoxide, turning it into hydroxide. Again, from an acid-base perspective, this reaction is going to have an equilibrium constant of close to 1. You can also do aldol condensations with ketones. So again, this is just an example of a net reaction. But two molecules of acetone, again treated with sodium hydroxide, can condense together to give a molecule of 4-hydroxy-4-methyl-2-pentanone. Once again, the new carbon-carbon bond that is formed during the aldol condensation reaction is indicated in red on this slide. So, like most carbonyl addition reactions, the aldol condensation is reversible with delta G close to 0. So that means we have to consider the equilibrium and which of the two products, the starting materials or the product, will be favored at equilibrium. So it turns out that with aldehydes, the equilibrium generally favors the beta hydroxyaldehyde product. Okay, so just a slight variation on the reaction that I introduced you to at the beginning of this lesson. In this case, we're going to use butyraldehyde instead of acetaldehyde. The aldol product will be present 75% at equilibrium. The starting materials will be present 25%. Notice this is not 100%. This is not a reaction that has gone to completion. And if you just let these things, one of these reactions go, in this case, you will have both compounds present at equilibrium. Letting it go longer does not change the equilibrium concentrations of each component as long as the reaction has reached equilibrium. With ketones, on the other hand, the equilibrium will generally favor the starting materials. Okay, so the self-condensation of cyclohexanone, to give an aldol product here, would favor the starting materials in about an 80 to 20 ratio. Okay, so we have seen that this is an equilibrium reaction, and when you have an equilibrium reaction, what that means is that at equilibrium, the forward reaction and the reverse reaction are taking place at the same rate. So we have already looked at the mechanism of the forward reaction. Now in our next lesson, we will look at the mechanism of the reverse reaction, which we also call the retroaldol.